So for today's session, we're gonna cover about right-angled trigonometry. It's mostly also the things that I think you mostly should have known about. Like, okay, before we start with like the chapters in the highest level, trigonometry means the study of relationships of side lengths and angles of a triangle in things that are related to it. So, as you may know, the common trigonometry would be like sin, cos, tan, theta. And we're gonna mostly cover about like the basics of it. So in a triangle, there's usually 3 sides, right? And if it's a right angle triangle, aka 90-degree triangle, and if there's an angle right here, the longest side of the triangle is usually called what you call as hypotenuse. And then the opposite of the angle, or like the one right in front of the angle, is called the opposite. While the one that's at the same, same side as the angle would be what you call as adjacent. And so in relation to sin, cos, and tan, you may have heard of this thing called Sohcahtoa, which is an easy way to memorize the sin, cos, tan formula. So sin would be opposite, sin theta would be opposite per hypotenuse. Well, cos theta would be adjacent over hypotenuse, and tan theta is opposite over adjacent. So the reason why it's like you have this formula actually has relations with how the sine value and the cos value and the tan value is graphed. So if you graph a sine value, let's just say y equals to sine x, it will look like something like this. Sorry, let me draw that in a nicer looking way. This would be pi, 2 pi. Yeah, I think this is correct. Oh wait, sorry. This is, I think this is pi and this is 2 pi. My bad.
Actually, you got it right the first time.
Wait, really?
Because 2 pi is when it completes one full rotation.
Yeah, but oh yeah, okay. Sorry, I think I mistook pi as 90. My bad. Pi is supposed to be 180, right? Yeah, and this is 1 over 2 pi, or 90 degrees. This is the radian form. So what's going on is that the sine wave, like its name, the sine wave, is a cycle of a repetitive wave. But I don't think we're gonna be covering that up later, like in this session, because highest math session, the math formatting is kind of weird. I think it's gonna cover in the future sessions though. Well, if you look at cos, it's It's like sine, but it's shift below. So you see, if it's sine is like this, right? But this one starts with 1. This one starts with 0 and then it goes to 1. So this is 1 over half pi, or 90. And then the next part would be 270, or 3 over 2 pi. And then for tan, the reason why it's opposite over adjacent is because tan is you can pretty much depict tan as sine over cos. So for the graph itself, it looks like something like this. Where this is 0, this is 90 degrees, this is 180, or pi, 1 over 2 pi. This is. And interestingly, this graph is also created by inputting sine theta over cos theta. Or in this case, it's sine x over cos x. But I don't think I should explain further than that, because I think that would be covered in the future sessions. Okay, so since we've covered about the general formula of it, we're going to go into the inverse functions of these trigonometric values. So sometimes you can see the sign is in form of -1, or maybe in like other cases it's called arcsine. So for example, we have this. So what's going on with this is essentially just what happens when you when you're trying to look for the value of theta. So for example, since you have sine theta over opposite for hypotenuse, if you want to try to look for the theta itself, you move the sign to the other side. And so you turn it into the inverse version of the sign, which is sine -1, or arcsine, or opposite for hypotenuse. For example, you have this triangle, and this is 3, this is 4, and you have this unknown angle. So how you find it is you insert the ratio of the opposite per hypotenuse, and you put in sine -1 per 3 over 5. And that's how you got. And you insert it in your calculator, and that's how you get the result. The result is, I think, I forgot. I don't remember these values. Let me insert it in the calculator. And you get you get 36.0 36.86 or 36.9 degrees. And it also goes the same for cos and tan. So for example, if you're trying to look for this angle using the cos, then you do cos minus 1, 4/5 equals to 36.9 degrees. And for tan, you do opposite over adjacent, which is 3/4, and you would get the same result. So since we've learned the basics of trigonometric figures, like the right angle, this right angle, and the sin costan, we can also apply that in other geometric figures to help simplify how you to help navigate and simplify how you try to work on finding the value of some geometric figures. For example, we have the isosceles or equilateral triangle, in which you can divide it into two, or let's just put dotted lines. So for example, in the case of the equilateral triangle, we have 60 degrees. And to make it more convenient for you to find, for example, we're trying to find the length of this, you can easily look for it by dividing the triangle into two. So you know the angle is 60, and then this is 30. And since you want to find this and this, you're going to have to this would be adjacent and this would be hypotenuse, so we can use cos. So cos 60 degrees would be adjacent over hypotenuse. Let's just say the hypotenuse is x. So cos 60 is 1/2 over half of x over x, and that gets you to I mean that pretty much shows that like let's just say like the adjacent is unknown and the hypotenuse is x, and cos 60 is 1/2, and that would get you 1/2 x as adjacent, which we can confirm, since if we pull it in half, then the length of it gets divided into two. And then for isosceles triangles, it can help with trying to do problem solvings with it in general by making it into right triangle. And there's also rectangles or squares. So in the case of rectangles or squares, since all the sides are 90 degrees, you can divide it into two, pull a diagonal on them, and it would turn into two right angled triangles. So for square or rhombus, if you were to pull their diagonals would be what you call as a diagonal bisection, because they meet they usually meet in the middle, the midpoint of their diagonals. And usually these midpoints of the diagonals are 90 degrees. So it turns into 4 mini triangles. On the other hand, we also have kites, where if you pull up their diagonals and have their intersections to meet, then their intersection would be right-angled triangles, would turn it into 4 small right-angled triangles. And then other applications of this would be when you have a tangent and a circle. If you pull a radius up to the point where the tangent meets the circle, then this would be a right triangle. This rule applies in anywhere of the triangle as long as it's a tangent and as long as you connect it with the radius, and it would turn into a right angle. And then we also have the circumstance when you have a diameter and you have a triangle in the circle. So however the triangle looks like, as long as it's a part of the semicircle and as long as the points meet the one diameter to another point of the diameter and they also touch the circle circumference, the triangle will always be a right angled triangle. The last one for the circle properties would be that if there's a chord is basically something like a line in the circle that's not touching the center of the circle. If you pull a line from the origin to the chord in the circle, then the line that's pulled is definitely gonna make a right angled triangle. And the line is going to be at the midpoint of the chord no matter what. Okay, so after we've covered about this, now we have problem solving with trigonometry. So one of the easy or common problem solvings that you have in trigonometry would be the angle of elevation or angle of depression. So usually the question would ask you, like, for example, like we have someone who's looking from the ground level and they're looking at a tree, like the top of a tree that has the distance of x, and the tree has for example the height of y, and then they ask you to find the angle of elevation. And it so angle of elevation is just like the floor when you look up, and they try to ask you like the degree of the bend of it. It is usually like you try to look for it using trigonometry. In this case, you use tan. Theta equals to y over x. And then there's also angle of depression. Like for example, if you're on a tower and then you look down, and from here you look down into something, they would ask you to calculate the angle of depression. Then that would be this part of the angle. In for example, if there's a bird here, and then they ask you a question about like the bird's angle of elevation from this position, then you have to calculate this angle, which is technically the same from this, and this is supposed to be the same. Yeah. And then the next part of it is bearings. So to have a true bearing, it should be measured clockwise. So from you start from north, and then you go clockwise. You only go one way. You never do anti-clockwise in bearings. And then the next is, like I said before, you go north, and it's usually in 3 digits. So for example, if you have bearing, you want to look for bearing B from A. Let's just say bearing B is right here. This is B, this is A. If they say bearing B from A, then they're looking for this angle. So usually the A is the origin of the bearing. And then the B is like the point that you want to try to look for the angle from A. So since this is a pretty small angle, let's just say this is 60. This is an estimation of it. Then if you want to write the bearing, then your answer should be 060 degrees. And in other cases, if you have a decimal bearing, for example, this is 40, let's just estimate this. Maybe this is 46.5 degrees. You'd say 046.5 degrees. This is fine. You can estimate it. And then there also like something like, for example, they want to look for the bearing of A from B, this one. Then the way to calculate it would be to look for the bearing, this part of the bearing. And using maths, we can know that 180, the total of this part and this part is 180 degrees, because it's like one side of a parallelogram or one side of a trapezium, and that results you in 180 minus 60 degrees, which equals to 120 degrees. And how you find the bearing of A from B would be to do 360 degrees minus 120 degrees, which would be 240 degrees. And then lastly, we have the angle between a line and a plane. So this is also pretty easy, and this is also fairly similar with the angle of elevation, except this is 3D usually. For example, if you have something like a cube, and then you have plane, you have A, B, C, D, E, F, G, H, and you want to look for a line in here, and then they ask you for the angle between the angle of line FC when the plane is ABCD, then that's like essentially asking you for the angle of between FC and AC, because it's kind of like, if you imagine this line, it kind of looks like a triangle, except the triangle is in the 3D shape. So you have to look for all the sides of the triangle, so you can finally find the angle between the line and the plane. And since all of these are mostly like theories, and that's it for the theory, we're gonna have to move to the high step book and work on some examples so that you can be more familiar with it. But technically, you should already be a bit familiar with it and already have learned all these concepts, because it's something, I think it's something that you're at least expected to know.